Okay, good afternoon, ladies and gentlemen. Today, my team and I will be talking about algebraic structures in cryptography. The team consists of me, I'll be starting off. Then we have Nanaku, Julius, Mauke, Martel, Yao, and Algebraic. So, I'm going to be starting with you guys off with the introduction to cryptography. So, we'll be talking about what it is, its importance, and some applications of it. And under that, we have the definition, confidentiality, integrity, authenticity, e-commerce security, protection of sensitive information, privacy in personal communications, and the evolution of cryptography. So for the definition of cryptography, cryptography is basically the science and art of encoding and decoding information for data security. It's like in cybersecurity, when you have information or you have some sensitive information, you don't want anybody to gain access to it, like any outside party or body to gain access to your sensitive information. So you can encode it so that it's protected, so that nobody can just gain access to it. Then it will go to the intended user, and the intended user can decode it. That's the whole point of cryptography. And some of the importance of the confidentiality. So it maintains confidentiality by ensuring that only intended recipients can access the information, as I just explained. So once you encode the message or the information, only the intended user can get it, and that person will decode it to be able to see what's inside. Then we go to the integrity. Cryptography ensures the integrity of data by protecting it from unauthorized contributions during transmission. It's basically the same thing. And authenticity. It verifies the authenticity of the information, confirming that it comes from a legitimate source. It does that through the encoding and decoding as well. Because if data comes to you and it's encoded, once you decode it, you can tell that okay, this is authentic information or data. Then e-commerce security. For e-commerce security and protection of sensitive information, that also falls under the encoding and the decoding. I'm sure you will understand that. The privacy in personal communications, exactly. So, evolution of cryptography. The evolution of cryptography has also led to sophisticated methods, integrating advanced mathematical concepts for enhancing security. So that's actually what we are going to be talking about, like with the algebraic structures in cryptography. It's like imbibing algebraic structures, which is the mathematical method, into the cryptography to enhance the security even further. So we are taking a step further into the future. So here are some key concepts and importance of algebraic structures in cryptography. So relevance in cryptography of like algebraic structures. Algebraic structures are fundamental to cryptography, underpinning secure encryption algorithms and key exchange methods. Then we go to the groups. So these are some algebraic structures that are inside cryptography. We have the groups, rings, and fields. So for the groups provide a framework for defining operations that preserve security properties essential for maintaining data integrity. And rings. The ring supports modular arithmetic, which is critical in various cryptographic algorithms, enabling operations on integers. Then we go to the fields. The fields facilitate necessary operations for efficient encryption and decryption processes, allowing for the manipulation of finite sets. Then the complexity of problems. The complexity of problems like disputes, logarithm, problems significantly enhances the security of cryptographic systems. So what this is saying is that like already take it like this. These mathematical models are quite complex or like difficult to solve. So you are taking the high level complexity of the cryptography and you are combining it with the complexity of these mathematical models. So that it's harder to crack it, so that you can't enter it. That's what makes it more secure. So that's basically what algebraic structures in cryptography is talking about.
So I'm Mauke, what you can present, and I'll be talking about the categories of cryptographic methods. First off, we have symmetric cryptography. This is where a single key is used for decrypting and encrypting data. And it also acts as a public and a private key at the same time. So an example of where symmetric cryptography is used is the AES algorithm, which stands for Advanced Encryption Standard. So over here, it's known to be efficient because it uses one key for everything, and you don't have too many keys or too many stuff in one place. So it uses that single key to decrypt and encrypt data. Then next we have asymmetric cryptography. This is where it uses a pair of keys. So a public and a private key encrypt and encrypt data. And an example of where this symmetric cryptography is used is the RSA algorithm, which stands for reverse Shamir-Adelman algorithm. Over here, it uses as I said earlier, it uses a public and private key pair to encrypt and decrypt the data. Next, we have hash functions. And the hash functions, you can also be seen, you can also be applied or seen in HTML or web development. This is where the password, like let's say you have a password field. Instead of, you don't want people to see the public domain to see the password. So use the hash functions or use the hash functions to hide them from the general public. So like let's say you have the password text field. When you're entering the password, it will come as either dots or a string of asterisks. So this is where this is an example is SHA, secure hash algorithm. This is used for data integrity checks and verification. So this ensures security and also doesn't make sure that people don't, other people or third parties don't see your private data. Thank you.
Hello, my name is Yalta, and I'll be talking in depth about small algebraic structures. So we're starting with group theory and its benefits in cryptography. So first of all, what's a group? A group is basically defined as a set that is combined by a binary operation. So it's only a single operation. It can be either addition or multiplication. And this group must follow 4 properties. The first one is closure. Closure simply means that if there's an operation between 2 elements in the group, the resulting element is also a member of the group. Then we have associativity. So that's basically saying that no matter how you order the elements, no matter how you order the elements, you get the same answer. Then we have identity. So identity is basically like, if we are doing multiplication as the binary operation, and you have element A being equal to 5, then your identity will be 1, because 5 times 1 gives you 5. So the identity works in a way that whatever number you multiply by, you get the same number back. And then finally we have the invertibility. So for invertibility, if you have, let's say 5, and then your operation is multiplication, you need to get a number that when you multiply by, you get 1. So the inverted 1, or a to the power minus 1, will be 1 over 5. So now, when it comes to the Diffie-Hellman key exchange, this method utilizes the multiplicative group of integers modulo p to facilitate secure key sharing between parties. So basically, it just enables 2 users to establish a common secret over an insecure channel. So they're able to share keys over an insecure channel without anyone knowing the specific key they are sharing. So this is an example. So let's say we have 2 people, or a number. They pick 2 public values. This value is known to everyone. It doesn't really matter because they can't do anything with it. Then they all pick 2 private keys that they only know. No one else knows about the individual themselves. So you put in the formula g to the power a modulo p. So your p here is a large prime number, and your g here is a generator. Your generator has to be lower than the prime number you have over here. So when you put it in the formula, Obor's private key was 6. So 5 to the power 6 modulo 23 gives you 8. Alvin's private key was 15. So 5 to the power 15 modulo 20 gives you 19. So now when you want to find the secret key that they will both be using to encrypt and decrypt, Obor takes Alvin's public key, that's 19, and then he raises it to the power of his private key, which is 6, modulo 23, which gives him 2. Now Alvin takes Obor's public key, raises it to the power of his private key, which is 15, and then modulo 23, which gives him 2. So in the end, they both get the same value. So that becomes the shared key, and they are the only ones who have access to this key, so no one else can access their advantage. Now, with the importance of group properties, the inherent properties of groups underpin the security of cryptographic systems. The difficulty of solving certain mathematical problems related to groups ensures the integrity and confidentiality of data. So with something like the RSA algorithm, it deals with factoring large prime numbers. And when you factor two large prime numbers, you get a composite number. And such numbers are hard to solve with normal mathematical issues.
Okay, so moving on from groups, we move to rings and fields in cryptographic systems. So first of all, what's a ring? A ring consists of two operations, addition and multiplication. So a ring is similar to just that over here you can use two operations, whereas in a group you can use one operation. So you can use addition, multiplication, subtraction. You can't use division because the element you get to be outside the ring. So when we come to fields, fields are algebraic structures that allow division, essential for finite field arithmetic, extensively used in cryptographic algorithms. So in fields you can use addition, multiplication, subtraction, and division, but you cannot divide by zero. If you divide by zero, the elements you get to be outside the field. So an example of using a field would be the AES, which is the Advanced Encryption Standard. So it operates over the finite field GF2. So a finite field means that the number of elements they are limited. So usually with finite fields or with a GF2, there are 256 elements, which means that if you are creating an encryption key, there are a lot of values, so it's safe and it will be hard to crack. So the importance of rings and fields in cryptography. Both rings and fields enhance the security and efficiency of cryptographic protocols, enabling complex operations vital for secure communications.
Okay guys, I'm Jerome and I will be taking on the advantages of elliptic curve in cryptography. Some of the advantages are security based, efficiency and application suitability. So when it comes to security based, the security of ECC is based on the elliptic curve respect, logarithmic problems. And that's a complex problem that enhances cryptographic strength compared to the one methods. It is more secure and it's harder to do anything, so therefore the information is more secure. The most efficiency. The ECC offers comparable security levels to RSA with smaller key sizes. For example, the 256-bit ECC key provides equivalent security to 3072-bit RSA key, resulting in faster computation. So this basically means that everything will be fast and efficient. One last advantage is application suitability. Due to the efficiency, ECC is particularly advantageous in environments with limited computational resources, such as mobile device implementation. Since it is very secure and very efficient, it's more easier to implement it in different situations, such as Internet of Things and mobile devices.
So another people will be speaking on the comparative analysis of cryptographic algorithms. So I'll be speaking on RSA, DSA, and ECC. So RSA stands for reverse sharing add-on. DSA stands for digital signature algorithms, and ECC stands for elliptic curve cryptography. So for RSA, it relies on the difficulty of factoring large primes. This is slower for decryption compared to the encryption, and it also uses key sizes for security. So usually it comprises from 1024 bits for 80 bits symmetric security, and 3072 bits for 2048 bits symmetric security. And then for DSA, it uses modular exponentiation, and it is faster for signing than RSA, and it is slower for encryption. And the key sizes for security are 1024 bits for 80 bits symmetric security. And under ECC, which is considered as the most effective out of the three of them, it offers high security with smaller keys. It is faster and more efficient across various applications. The key sizes for security are 160 bits for 80 bits symmetric security and 256 bits for 2048 bits symmetric security. Okay, so as I said already, the ECC is considered as the most efficient out of the three cryptographic algorithms because it offers higher security with smaller key sizes. The RSA is mostly used for digital signatures and encryption. The DSA is mostly used for just digital signatures, and the ECC is versatile and used for both encryption and digital signatures, which is why it is considered as the most efficient out of the three.
So I'm curious and I'm taking you guys through future challenges in cryptography due to the development of quantum computers and quantum systems. So one challenge that may arise is just classical algorithms. You all know quantum computers are very powerful and can solve problems much faster than regular computers. So cryptographic methods like RSA and DCC, you can't ban out because this quantum computers will crash it. So another challenge is post-quantum cryptography. That's PQC. So to address this problem, scientists, mathematicians, and researchers are developing new types of cryptography called quantum resistant algorithms, which can safeguard systems. Last, the importance of adopting PQC. To safeguard sensitive data against the inherent threats posed by quantum technologies, organizations must practice the use or implementation of PQC solutions in their cybersecurity strategies.
Okay, so I'll also be talking about the role of algebraic structures in cryptography and key insights for future development. Firstly, we have algebraic structures are crucial for cryptographic algorithms. So these mathematical frameworks underpin the security mechanisms that protect sensitive information in digital communications. Secondly, they provide the necessary mathematical properties for secure communication. So properties such as the groups, fields, and rings are essential for creating robust encryption methods. Thirdly, we have ongoing research is essential due to advancements in quantum computing. So with this, as quantum technology evolves, traditional cryptographic methods face potential vulnerabilities, necessitating innovative approaches. Lastly, transition to post-quantum cryptography is vital for data security against new threats. So with this, developing new algebraic structures that can withstand quantum attacks is imperative for ensuring future. So lastly, transition to post-quantum cryptography is vital for data security against new threats. So developing new algebraic structures that can withstand quantum attacks is imperative for ensuring future data integrity.